All right. So good morning, distinguished guests, judges, CM, and MathWorks staff. My name is Jason Bao, and we are Team 14482 from Johns Creek High School, and we welcome you all to our presentation about defeating the digital divide. In this three-part problem, we first predicted the cost of bandwidth per megabits per second in the US and the UK over the next 10 years, and then predicted a household's internet needs based on the factors of age and household income level. Utilizing this background, we modeled the distribution of broadband nodes to maximize the coverage in three hypothetical regions. Regarding global assumptions throughout the whole paper, we first explicitly defined bandwidth as average download speed for clarity and standardization throughout the presentation. Next, we assumed that new revolutionary advancements would not occur in the next decade because there is really no viable way to predict the development of new advancements. And finally, due to the unpredictable effects of different environmental conditions and the rarity of sudden environmental disasters and surges of population density, we ignore the impacts of these factors on internet infrastructure and connectivity. So, in part one, we focus on determining a model for predicting the price of megabits per second by dividing the projected plan price over the projected bandwidth download speed in 2030. Our first assumption was that prices of 4G and 5G will remain equal over time because current consumers are allowed to switch from 4G to 5G free of cost, a trend that we assumed will continue for the next decade. Our second assumption was that differences in broadband prices between different providers were negligible due to the consistency of market share since 2015. So it's really unlikely that one provider will monopolize the market and dictate prices. And because of this, differences in plan prices are negligible, we assume that consumers will pay the same prices for their wired and wireless plans for the next decade. And finally, since data about US wireless plans was unavailable, we drew a comparison with the available UK's wireless plan prices and noted that the prices of US mobile internet was 1.86 times greater than UK mobile internet prices, so we applied this relationship to wireless plan prices.
For our model development, we first developed a general equation for calculating the average price per Mbps, which considered both wireless and wired plans. In this equation, we divided the average plan prices by the average plan speeds in order to find the average price per Mbps for both wireless and wired plans. We then multiply these by the proportions of total plans that are wired or wireless respectively in order to calculate the final average price of all plans. Since we needed to create a model that displayed change over time, we found equations for the variables of average plan speed, average plan price, and plan proportion and plugged them into our general equation. Here, we found data on US wireless and wired prices over time, plotted it in Excel, and used exponential lines of best fit on this data as our US wired and wireless price equations. As stated in our local assumptions, we assumed that US wireless prices were 1.86 times those of the UK. Here, we use the same process to find the UK wired and wireless price equations. We used this plot to find equations for the average speeds of US and UK plans. Since there's no evidence to suggest that wired and wireless plan speeds are different, we combined the wireless and wired speeds into one equation. With the formulas for average speed and price, we now take a quick detour to determine the proportions of wireless and wired plans over time. We found data that showed that wired plans are likely to increase by 5% each year, while wireless plans are likely to increase by 3% each year from 2020. So by using these values, we created equations for calculating these proportions over time. Using 0.317 and 0.683 as our base proportions, we then multiplied each by the yearly factor of change to the power of x, where x represents years from 2020. By dividing each of these values by their sum, we effectively found the proportions of wired and wireless plans over the next 10 years. After plugging in these smaller equations into our general equation, we were able to create a model using Python, and shown here are our final results. This model shows decreasing exponential curves for average price per Mbps in both the US and UK, with US prices decreasing at a greater rate. As shown by our model, by 2030, the average price per Mbps is $0.102 in the US and $0.224 in the UK. The key takeaway of our sensitivity analysis is that deviations in our proportional yearly multipliers, which represent the growth of the number of wireless or wired plans, lead to massive deviations in our results. We found that this is due to the fact that our model is exponential. As such, over several years, these deviations will lead to wider and wider offsets in our results. As for strengths of our model, it is fundamentally centered around historical trends. It is accurate, short-term results, and excludes extraneous variables like materials and labor, which can complicate and skew results. And it accurately recognizes prices should decrease over time due to factors like improving technology and accessibility. However, as for weaknesses, we struggled to find adequate data, so our assumptions had to fill in these gaps. Also, since our model used exponential curves, we found that small offsets in certain constants did not greatly affect our model in the short term, but could lead to large deviations in the long term. However, we do believe that using exponential curves is necessary. This is as we found it unlikely that over several years, the rate of change for factors like plant prices or plant speeds would remain the same. In addition, when using linear curves, we found that some of our graphs would hit negative values by 2030, which is impossible.
In part 2, bit to bit, we developed a mathematical model to determine how much bandwidth different households would require based on given characteristics. These were our assumptions to manage the complexities in the problem. Our first 4 assumptions are reasonable assumptions which have a negligible impact on the overall outcome, but help simplify the problem into reasonable parts. The final assumption is justified as 1, different age groups and different household income groups have different interests on the internet and different access to resources. In its simplest form, this was our model development. We utilized data to come up with weights for age and household income. Then we determined the total amount of time spent on bandwidth using activities with those weights. We found total data consumed by multiplying bandwidth consumed with time spent on the internet. And finally, dividing total data consumed by total time spent on the internet, we were able to find our bandwidth requirement predictions. These were the specific activities we defined as being internet using activities. And now I'll go into our model development in more detail. Our first step was to find the total amount of data that individuals were using on their internet using activities, with total data for an activity equals the time on an activity multiplied by the bandwidth required for an activity. This split the problem into 2 parts. First, time. We had to determine how to predict how long different individuals would spend on internet using activities. To do this, we performed linear regressions on Nielsen's data on internet activity by different demographics. Age, then household income was our respective independent variables, and time spent on the activity was our dependent variable. Linear regression was utilized because the Nielsen data, when graphed, appeared to lie in a straight line. This gets us the values for m in the equations. By comparing the magnitudes of the slopes of lines of best fit, that's the bottom equation, we were able to create a relative weight of importance to assign to each characteristic. With our calculated relative weights, we estimated that the time an individual spends on any given internet activity was how much time the demographic data indicated they would spend on the activity multiplied by that demographic's calculated weight. This way, we were able to conduct multivariable analysis from single variable data. And here, in practice, that process looks like this. We multiply the weights listed in the second column by its respective entry highlighted in yellow on the top table. Then the same with the third column and bottom table. These results are added in the fourth column, which indicates our prediction for how much time is spent on any given activity. In our first equation, we had data equals time multiplied by bandwidth. And prior to this slide, we covered how we calculated the time part of that equation. This table covers the bandwidth part of that equation. We researched the bandwidth consumption of our 5 bandwidth-consuming activities, and we present the values we use for average bandwidth consumption for each activity in this table.
Now that we have calculated the time spent on each activity and the bandwidth required to support said activities, we can then multiply them together to obtain the amount of data an individual will consume. The equation, which you see on the screen right now, works because it multiplies time, which we obtained a few slides ago and then converted to seconds, by bandwidth in megabits per second, leaving the variable d, or data, in terms of megabits. But we are trying to find bandwidth, not data. So we added the individual data requirements of each person in the household, and then divided that by the total time spent on the internet by everyone in the household. The number we obtain, b, is a raw number, an estimate of the average bandwidth a household will need at any given time in megabits per second. We also wanted to account for variability, given that multiple people could be using the internet at the same time, or could be consuming more bandwidth-intensive activities. So we added a random parameter, p sub std, in order to overestimate the bandwidth requirements according to the following equation: 0.2 times bandwidth, which we calculated on the previous slide, times a z-score. We selected 20%, or 0.2, as a reasonable percentage of variability, and our z-scores correspond to z-scores that would capture 90 and 99% of the area of the standard normal distribution in order to capture the household's needs with 90 and 99% effectiveness, respectively. Add this variable p sub std to our initial bandwidth calculation, and then divide that by 50%, and we have calculated the final average bandwidth requirements, b star. We divided by 0.5 because advertised Wi-Fi speeds usually overestimate the actual internet speed of a household by a maximum of 50%. With this extensive procedure finally complete, we can look at the results of our 3 given situations. These tables sort by time spent per person per activity, which we then added together and ran through the model to obtain our final values. Situation 1, which provided internet to a young couple with a 3-year-old child, output the second highest average megabits per second. Situation 2, meanwhile, which focused on a retired senior citizen living with her 2 grandchildren, output the lowest average bandwidth speed. And finally, situation 3 was the highest, which makes sense since we needed to provide internet to 3 undergraduate college students. We found these results and order to be fairly logical, especially the fact that all 3 situations called for roughly the same amount of bandwidth. This makes sense, because even if a college student might use Netflix or Hulu for longer than a retired grandmother, those kinds of activities are outliers in regards to average bandwidth consumed by an individual or a household. This means that bandwidth per person should be roughly the same, and since each household contains 3 people, bandwidth per household should also be fairly similar. Now moving on, our sensitivity analysis analyzed one variable, p sub std. Changing p sub std, our random parameter, had very minimal effects, with a maximum percentage change of 1.6% corresponding to a 5% change in p sub std. The biggest implication of this is proof that our value of 20% is a reasonable percentage of variability. In summary, our approach of dividing total data by total time and then accounting for variability was mostly quite successful. It incorporates online data regarding both time spent and bandwidth required for 5 activities, so our coefficients and variables have a basis in real numbers. In addition, our sensitivity analysis proves that the addition of new data or changes to existing data will not meaningfully affect our results, again indicating the model's strength. However, we could have ensured further accuracy by breaking our list of 5 activities into even more specific subsections, but this was limited by the relative unavailability of that data. In addition, there's still risk that we have underestimated bandwidth requirements, since intensive activities like video streaming would definitely require more bandwidth than our calculated averages of 3 to 4 megabits per second, especially if multiple people are using the internet at the same time. However, given that we are calculating averages in this model, and most activities require much less than 3 megabits per second, our calculated averages are still generally correct, even if our model was not as successful at correctly describing the distribution of bandwidth usage.
In section 3, we were tasked with creating a model which can determine how many broadband cellular nodes should be placed in a particular region and what type of band frequency they should output. We were then asked to apply our model to a series of provided example regions with a set of subregions. To manage the complexities of this problem, we made 3 basic assumptions. First, we assumed that nodes would be placed in an optimal location, such that each node covers the maximum distance possible with minimal overlap. The second assumption was that each subregion would have a uniform population density, as our provided subregion data does not specify the population distribution. And finally, we determined that the median age and median income would appropriately represent the entire subregion population, as these were the only 2 values which were given for every single subregion. Our model has 2 fundamental parts. We began by retrieving the median income and median age of a particular subregion. We then take these values and input them into our part 2 model, which outputs the bandwidth requirement for this median individual. Lastly, we multiplied this bandwidth requirement by the population of the subregion to find the total bandwidth requirement of this particular subregion. The second part is now determining how many nodes we need and what type of band frequency they should output. There are 3 types of band which a tower can output: high, medium, and low. A high band node will have a smaller providing radius than a low band, but will be able to meet a higher bandwidth requirement. Because we assume a uniform density, it makes sense for only one type of band frequency to be implemented in all the nodes in a particular subregion. We begin by calculating the number of high band nodes which would be required to supply the entire bandwidth in the previous step, and then determine the number of nodes which would be required to cover the entire area. This process is then repeated again for medium and low band nodes. Whichever band outputs the lowest number of nodes is the one we choose to implement. Our output can be seen now. As we can see, our model predicted that each subregion should implement somewhere between 1 and 5 high band nodes. But let's see what this actually means. Basically, we can see that our subregions are densely populated, so that the main bottleneck is really the bandwidth.
1 minute.
Therefore, a few high band nodes are able to meet the required bandwidth and cover the total subregion area. On the other hand, medium and low band implementation require more nodes than high band in order to meet the bandwidth requirements, and that the larger radius of the medium and low band was not beneficial. In analyzing the strength of our model, we observed that the model correctly predicted that areas with high population density would be best suited for high band nodes. However, a weakness was that it only uses median income and median age of a population to determine the entire bandwidth requirement. In the future iterations, we would like to incorporate other factors which would allow us to better model variable population distribution. From beginning to end of this challenge, we aim to use simplicity to tackle key aspects of the problem. Thank you for taking the time to attend our presentation. We'll be happy to answer any questions you may have now.
Thank you. Awesome job.
Thank you.
Okay, so I think we have some questions.
Yeah, thank you. That was really good. I have a question about the distributions you're using for question 2. You use a standard deviation based on the 20% of an average household. So first question is why the 20%, and what would you do to maybe refine that if you had more time? But also, you use the same standard deviation for every household. I'd like for you to comment on that and ask why is that reasonable, and what might, if not, what would you do to improve upon that?
All right, thank you. That's a great question. So first thing, we chose 20% as a reasonable percentage of variability because we estimated around, also according to our data, that advertised internet speeds usually overestimate the actual internet speed by 20 to 50%. So we selected anywhere between 20 to 50% as a reasonable parameter. And actually, as our sensitivity analysis shows, changing that value of 20% doesn't meaningfully affect our results. So ultimately, we just chose that as a reasonable value. And then regarding the distribution of each specific situation, we actually, so our standard normal distribution assumed that a standard deviation was 1. And so we calculated our z-scores according to that standard normal distribution with a mean of 0 and a standard deviation of 1. Because of that, I think we definitely could have improved the model by more accurately researching each situation and describing the specific distributions, which also in likelihood is actually skewed to the right instead of a normal distribution. And that's definitely one of our biggest weaknesses that we could have improved on going forward.
Excellent, thank you.
I have a question about question number 2. Somewhere there's a table that you guys have when you talked about sort of how much bandwidth for different activities. And I think you have like a TV connected internet device requiring 6.5 megabytes per second. I don't. Like that's a pretty common thing to do, sort of be streaming some TV. And so if that takes 6.5 megabytes per second, but then the households, like when you computed those values, I think the largest need was 3.8 megabits per second. So does that mean that no one can watch TV?
No, that means that we've actually calculated an average bandwidth requirement, which, as we mentioned, our model doesn't really account for when there's multiple people using the internet at the same time, which we attempted to estimate as best as we could. But we're actually calculating the average because for the most part, like using your phone or even playing video games on a TV requires much less than 3 megabits per second. And then those activities like TV streaming, like on Netflix or Hulu are actually outliers. So our averages, we think, are generally correct. And this was a deliberate choice that we made. Either we could have overestimated by making our means correspond to like the highest possible bandwidth requirement, or we could have underestimated. And we chose to underestimate and then account for this underestimation by then trying to overestimate with our random parameter p sub std. This is why we added it and then divided by 0.5. We understand that while all the time you're not going to need 3.5 megabits per second, sometimes you're going to need more. On average, a household is going to need around 3 to 4 megabits per second.
Okay, I also have a question for you about your solution for question 2. And I was looking at your paper. This is a table that I didn't see appearing in your talk, but when you determine the relative weights for your demographic factors, could you just comment on, the implication or the difference between negative and positive values in that table?
The difference between negative and positive value in the table would be that a negative value for age would indicate that as you get older, you become less likely to participate in this activity. And then like if it's positive, then as you go up in age, you are more likely to participate in this activity. And then similarly for household income, as household income increases, you are when it's positive, you're more likely to spend more time on this activity. When it's negative, you're more likely to spend less time on this activity. The reason we thought it was acceptable to use magnitude, so we didn't have to worry about the difference between like positive slopes and negative slopes, was since we were comparing the relative impact that the demographic category has on media consumption, that even if one was positive and one was negative, the relative strength between those positive values and negative values should still matter more than whether they're like positive or negative themselves.
Okay, so in your model, did you just take the magnitude of those numbers?
Yeah, we took the magnitude for
Okay,
these
all right.
numbers.
Thank you.
What other questions do people have?
I had a question about one of your assumptions. So I think you made an assumption that the like week-to-week internet usage was constant by week. And I'm wondering if there are any reasons that assumption might not hold. And if there are cases when it might not hold, how could you have accounted for that in your model?
Certainly, one of the things we were discussing when we were tackling this problem was how we would deal with like weekends and holidays. Since on those days, you would expect that like intuitively, you would assume that since there's more time to spend on the internet, that these households may spend more time on the internet on holidays, such as I guess like school breaks. In the end, we decided that it would not be a large enough factor to like base our model around. But if we were to improve our model to include stuff like that, it would be in the place where we took our standard deviations. And again, as Mehul was talking about, we assumed that the data would be normally distributed, but after further analysis, we've come to the conclusion that it's more likely skewed in a direction, which would help combat that.
Okay, great, thank you.
Hi, this is Cleve Moeller from MathWorks. I'm having trouble understanding about these sort of averages for the bandwidth. If I watch a movie once a week, my average bandwidth is not very high. But when I'm watching the movie, I need that high bandwidth. What can you explain to me the difference about averages and maximum needed?
Yeah, of course. So actually, one of our global assumptions that we made is we actually define bandwidth as the average download speed, because that's the generally accepted definition of bandwidth speed. And so we thought to use that type of reasoning throughout our presentation. And so while you might be like streaming Netflix or Hulu, that would be your peak internet speed. Which we haven't necessarily accounted for because we wanted to just gauge the general average of how much each household will need overall instead of the peak that they would need, which is why, again, we decided to underestimate and then account for its underestimation by adding our random parameter p sub std. And so while it doesn't fully account for the distribution of internet usage, it does accurately define the average bandwidth you would need over a given week or a given year.
Last night at the Academy Awards, in an ad, Xfinity announced that they were going to have gigabit Ethernet, 1,000 megabits. Do you have anything like that kind of speed in your models? And is Xfinity, are they going to have any customers with that speed?
There may be, but we wanted to actually calculate like how much bandwidth the people would actually use, not what kind of plan they would buy. And in our part one, we did actually like estimate the cost per megabit per second, which definitely accounted for the decreases in price with the increases in speed, since that kind of gigabit internet is definitely going to become more common over the next 10 years. But for the purposes of part 2, we just decided to focus on the actual bandwidth that would be used, not the bandwidth that would be bought.
Also going off of what Mehul said, one of our, I'm not sure if it's a local assumption or global assumption we made for part 1 was that we cannot predict the advancement of new technology. There's no constant rate. Sometimes it's exponential development, sometimes it flattens out. So there is no viable way for us to predict the development of new technology, such as this gigabyte Ethernet. Because of this, we're unable to predict just the production of new technology. So we assumed it was negligible.
I can go ahead and ask one question of the whole team. We have just a few more minutes left. What was the most challenging part of that day when you were coming up with your solutions?
I guess one challenging part was finding data. I guess this is kind of relatively new topic that a lot of times we didn't have specific data to gauge on. So we had to kind of model predicted data, or we had to kind of use relationships. Like for our wireless plans in the US, that data wasn't available. So we had to use a comparison with internet prices to gauge the projected price of US wireless prices.
And also we were working as a team on this virtually. So it was a different dynamic than when we competed last year and we were all eating pizza together in one room. So it was an interesting year.
Well, it doesn't really show it on our presentation, but part 3 required a lot of calculation, and that was kind of a pain, but otherwise it was pretty smooth.
Yeah, I guess for me, just the biggest thing was, there were so many different ways that you can define internet and so many different ways you can approach how to provide internet to the people. And so like the approaches we chose were definitely like deliberate choices that we made. And like if we had taken a different one, then a lot of our like biggest strengths from this model wouldn't have been transferred into that like new choice. And so we had to make like a lot of decisions as to what exactly were the factors that we wanted to focus on. And that's why like one of our biggest goals like throughout the presentation was just like focusing on like the key aspects and aiming for simplicity wherever possible.
All right, I'd like to thank our speakers one last time. You did a tremendous job and we're very happy to have you here, so thank you.
Thank you.
Thank you.
Let's see, I believe we need to head out and work with the next team, but we will hope to see you very soon and hope to see you at the final presentations later today.
Thank you so much.
Thank you.
Thanks.
Thank you.
Great presentation. Thank you.
Great job, guys.
Thanks a lot. Good job, guys.